Okay, so we're going to talk about something called formal charge, and I also wanted to just touch on some exceptions to the octet rule, except they're in your textbook in section 4.8, exceptions to the octet rule. I am not going to cover any of them. I will not ask you about any of them on the exam, but they are in section 4.8 in case the SmartWorks homework asks you anything about them, or in case you need to know about them anytime in the future. This is not something I will ask you about on the exam, both formal charge and the octet rule. I won't ask you any questions about them directly on the exam, but you might need them for some parts of other problems. So I wanted to at least touch on it so you'll have that information. So first we're going to talk about formal charge. So what is formal charge? So formal charge shows the charge distribution within an ion to verify the best Lewis structure. Okay, so sometimes there will be more than one Lewis structure that technically makes sense. So you would use this process of formal charge to determine which is the most correct. The formal charge should equal the charge on the molecule or the ion. I should say the sum of the formal charge. So the sum of the formal charge should equal the charge on the molecule, which is 0, or on the ion, which could be whatever the charge of that ion is. So here is the step to solve for formal charge. So formal charge, Fc, equals the number of valence electrons minus the number of unshared electrons plus half the number of electrons in bonding pairs. Half times the number of electrons in bonding pairs. Okay, this seems confusing, so let's do an example. Examples are always the best way to explain a new process like this. So let's go back to carbon dioxide. So we already have drawn the Lewis structure for carbon dioxide, but let's see something else. So carbon dioxide, CO2, it has carbon, which has 4 valence electrons, oxygen, which has 6 valence electrons, times 2 is 12. I have a total of 16 valence electrons to distribute. So we went through the example and we saw that carbon dioxide looks like this. And 2, 4, yeah. So that is the Lewis structure for carbon dioxide. However, this also works. Okay, so here, in both of these situations, all of the octets are satisfied. I have distributed 16 electrons, and all of the atoms have a full octet. but these are not equivalent Lewis structures. This one is correct. This one is not. So the formal charge should equal 0 because this is a neutral molecule. So let's see what the formal charge is. So you determine the formal charge on each of the atoms, and then you add them up to see what the best formal charge is. So the best formal charge is where the sum is 0 or where each is 0. In this case, because it is a molecule that's charged, that's neutral, we want it to equal 0. So for each of these, we're going to say the number of valence electrons. So for oxygen, oxygen has how many valence electrons? It has 6, minus the number of unshared electrons, so 2, 4, plus half the number of electrons in bonding pairs, 2, 4. So half times 4 is 2. So half times 4 is 2. 2 plus 4 is 6. 6 minus 6 is 0. So the charge on this oxygen is 0. These two oxygens are exactly the same, so that means the charge on this oxygen is also going to be 0, but I'll write it up here again. 6, the number of valence electrons, minus the number of unshared electrons, plus half of the number of electrons in bonding pairs equals 0. So the formal charge on both of these oxygens is 0. So far so good. Let's now look at carbon. So the number of valence electrons, 4, minus the number of unshared electrons, 0, plus half the number of electrons in bonding pairs, 2, 4, 6, 8. Half times 8 is 4. 4 minus 4 is 0. This has a formal charge of 0. 0 on this oxygen, 0 on this carbon, 0 on this oxygen. So this is the best Lewis structure. This is why. Let's see why this is a not acceptable Lewis structure. Okay, so let's do this one. Oxygen. It has 6 valence electrons. 6 minus the number of unshared electrons, 2, 4, 6, plus half the number of electrons in bonding pairs, 2. Half times 2 is 1. 1 plus 6 is 7. 6 minus 7 is -1. So the charge on this oxygen is -1. So now let's look at this carbon. Carbon has 4 valence electrons minus the number of unshared electrons, 0, plus half the number of electrons in bonding pairs, 8. Half times 8, half of 8 is 4. 4 minus 4 is 0. The formal charge on that carbon is 0. So now let's look at this last oxygen. So 6 is the number of valence electrons that oxygen has, minus the number of unshared electrons, 2, plus half the number of electrons in bonding pairs, 2, 4, 6. So half times 6 is 3. 3 plus 2 is 5. 6 minus 5 is +1. So this is not the correct Lewis structure, because the correct Lewis structure is the Lewis structure where the formal charge on each atom is 0. It's 0 because this is a neutral molecule. So we want the sum of these to equal 0 because this is a neutral molecule. If this was a polyatomic ion, we would want the formal charge to equal the charge of that ion. So for example, if we were looking at the carbonate ion, which has a charge of 2-, we would want the sum of these to equal to -2. So this is how we use the octet rule. This is how we use the formal charge. And formal charge is used when there is more than one possible Lewis structure that will satisfy the octet rule, but there's one that is more correct, and that is the one that has a formal charge of 0 on each atom. Or if it is an ion, the sum of these formal charges would equal the charge on that ion. So exceptions to the octet rule, I do want you to understand that there are exceptions to the octet rule. So we know hydrogen wants 2, and then everything else wants 8. But there are some exceptions. So you're going to see some exceptions in some of the problems that we'll cover later. But I won't ask you to memorize them or ask you about those specifically. And again, that is in section 4.8. So these are atoms that can have more than 8 electrons in their outermost shell, or they can have either an expanded or a reduced octet, it's called. So boron, for example, is happy with 6 electrons in its outermost shell. Phosphorus can have 10 electrons in its outermost shell. Sulfur can have 12 electrons in its outermost shell for these expanded octets. So there's lots of examples of exceptions. I won't give you any of these without an explanation that it is an exception to the octet rule. So some of the Lewis structures for these are going to look a little different. They are in your textbook. You might see them in SmartWorks, but for an exam, I would tell you that it was an exception or do a different example.